Okay, let's talk about percent composition. And when I say percent composition, I mean percent composition by mass, as opposed to a percent composition by volume. In chemistry, a lot of times that's what we're focused on is mass measurements, most things. So when we talk about percentages, unless if you're told otherwise, you should assume it's a percentage by mass, meaning it's calculated based on a ratio of masses. But there are some scenarios where you would look at percentages by volume. But if we do that, I would specify that it's by volume. So whenever you see a percent, assume it's by mass, unless if you're told otherwise. So percent composition is just the way we would normally say it. And what we're talking about when we say that we have the percent composition of something or we want the percent composition of something, we're talking about the composition of a particular substance expressed in terms of percentage of each component. Okay, so for a compound contains multiple elements, and if we want the percent composition of that particular compound, we're going to communicate it in terms of the percentage of each element within that compound, okay? And we'll do it in terms of masses. So the reason we would do this is because this is a piece of information that is constant no matter what your sample size is. If you're talking about a particular substance, that substance is always made up of the same proportions of things, right? Because we have the law of definite proportions. And so when we look at a percent composition, if it's for a particular substance, it's always the same. So we can apply that to any sample of that substance. And so that's what makes it kind of useful. Just like a molar mass is constant no matter how much or how big of a sample you want to apply it to. You can look up the molar mass of that compound and apply it to figure out how many moles or how many grams you have. So to convert between those things, we can use percent composition similarly because it is something that is specific to whatever substance you have, and we can use it to do conversions. And so first off, before we utilize it to actually convert between things, let's look at how you would actually calculate it. Now there's kind of two ways you could do it. It just depends on what information you have. So one way is if you actually had a real sample and you were able to break it down into the component elements. Okay, so say you took a compound and you broke it apart into the individual elements and were able to separate those out and measure how much of each you had. Then you could take the individual amounts and divide each of those by the total mass of the sample, and then you multiply by 100 to make it into a percent, okay? So it's a ratio of masses times 100 to make it into a percent. So most of the time you see it as written times 100%. You're multiplying by 100 and the percent portion of that becomes a unit. Okay, so you can do this with data from a particular sample, okay? But most often when we calculate a percent composition, we do it using molar masses, okay? So you can look up the molar mass of component elements and a total sample by using the periodic table, right? So you can look up in the periodic table the mass of each thing that makes up that substance, and you could sum up the total mass of that substance, and you can take the ratio of those things, okay? And so you take that ratio, and you actually, excuse me, you actually divide those numbers, and then you multiply by 100, and it becomes a percentage, okay? And you would do that for each individual element contained in that compound, okay? So let's look at an example first of how we would do that. So let's look at magnesium silicate, okay, Mg2SiO4. So I want the percent composition of magnesium silicate. So you can go about this in different ways, but basically we have, we have magnesium. So we're going to want a percent of magnesium, right? And we have silicon. So we're going to want a percent of silicon. Okay, and we have oxygen, so we're going to want a percent of oxygen. So we need to find a percent of each of those things. And we do that by putting the mass of the particular thing we're focused on. So in this case, the mass of magnesium, we're going to put on top, and then over the total. So the mass of Mg2 SiO4. Okay. And then we're going to multiply by 100 to make it a percent. Okay, we're going to do the same with silicon. We're going to put the mass of silicon on top, and on the bottom, we're going to put the mass of magnesium silicate. And then we're going to do, and multiply by 100, then we're going to do the same thing with our oxygen. We're going to have the mass of our oxygen over the mass of the Mg2SiO4 compound, okay, times 100, okay? So that's your basic setup, and it's the same for any type of compound. You put each individual substance over the total mass, okay? If you had actual masses of a particular sample, you can use that. We're going to use molar masses. So we're going to look at the periodic table and look up magnesium, and magnesium is 24.31, and that's grams per mole. But then you look at the formula and there's 2 of those. So I need to multiply that by 2 because I want all of the magnesium in that particular compound. Okay, and I'm going to put that over the total mass. Okay, now you could first total the mass. I'm just going to do that as we go. So at the moment, I'm going to leave that bottom number blank, and I'm going to go ahead and get these others because then I just need to add the top numbers together. Now silicon, if you look at the periodic table, it is 28.09 grams per mole. And in one of these, I only have 1 silicon, okay? And so that's going to be over the total. Again, I'm going to leave that total blank at the moment, and I'll add those up once I have them all written down. And then the oxygen, each oxygen is 16.00 grams per mole. And in that compound, there's 4 of them. So 4 times that. And again, over the total. Okay. So I waited to do the total just because I knew I was going to have each individual component written down here. So I have them all written down. So if I take the 2 times 24.31, so that's going to be my mass of magnesium, I add that to the silicon, so the 28.09. And then I'm going to add that to the oxygen. So 4 times 16. And that's going to give me the total. And the total ends up coming out to 140, oops, it's supposed to be a 4. Like that, 140.71 grams per mole. Okay, and then all of this is multiplied by 100 to make it into a percent. And so we're going to divide all of these by the 140.71 grams per mole. And then all of them get multiplied by 100 to convert them into a percent. If you don't do that final step of multiplying them by 100, you're just calculating what we would call a fraction. And so it would be a decimal value. You would get point something, okay? You multiply by 100 to shift the decimal place and to make it into a percentage. And so go through and calculate, oops, each one of those. So I'm going to take the 2 times the 24.31, I'm going to divide it by 140.71, and I'm going to multiply that result by 100, okay? Now I'm going to round all these to 4 sig figs since all my molar masses of the individual elements are 4 sig figs. And depending on how many sig figs you take from the periodic table would really determine your sig figs on this. But you should always keep at least 2 decimals. from the periodic table. So your percentages should typically always come out in 4 sig figs or more. So we have 34.55% magnesium. Okay. And then, so that's one of the percentages. And then I've got 28.09, and I divide that by 1.71 and multiply the result by 100. And that gives me 19.6% silicon. And then, let's see, 4 times 16 divided by 40.71. Multiply the result by 100, and I get 45.48% oxygen. Okay, so those 3 percentages together, that's called the percent composition. Okay, so that's the percent composition of that particular compound. Now, you can always go and kind of check to make sure at least you didn't make any major errors. If you add these together, so I take 34.55 and I add 19.96 and I add 45.48, you really should get 100. Depending on how much rounding is done throughout, it can be a little off. So when I add these together, I get 99.99%. And so it's close enough, okay? It's really close. And so there's a little, if I would have rounded a little less throughout my calculations, I would have actually got 100%. But that's pretty close. That's about 100%. That's good enough, okay? If you come up with something like, 95% or 80%, something's definitely wrong, okay? It should be 100% or very close when you calculate this percent composition for each element in some compound. So you should be able to quantify the percent composition of compound, whether you have an actual, sample that you broke down into the elements, or if you just use the periodic table. Either way would give you the same composition breakdown for this particular compound. Okay, so each compound has its own unique percent composition. Okay, now once you have a percent composition, so a percentage breakdown of a compound, you can actually utilize that information to create conversion factors. Okay, factors that then you can use in dimensional analysis to convert between the mass of the individual the individual components and the total compound. Okay, so if you knew how much compound you have, you can quantify how much of an individual element is in that sample using the percent composition. Or if you knew how much of a particular element you wanted in your sample, you could quantify how much of the total sample you need. Okay, so you can jump between the total compound and the individual components using the percent composition as a conversion factor. So what you need to remember is a percent is always an amount per 100, meaning a value over 100. Okay. So really, when we're talking about a percent composition or mass percent, it gives the number of grams of whatever it's the percentage of per 100 grams of the compound. Okay, so let's say, for instance, I give you an example over here. If we have a percent composition of compound AB, okay, so just some generic compound. I have compound AB, and I tell you that it's 25% A and it's 75% B, okay? And if I don't tell you otherwise, those percentages are mass percentages, okay? That's what we're talking about. Then I can rewrite those pieces of information as conversion factors. So if I rewrote those, I could write them as 25 grams of A per 100 grams of AB, or 100 grams of AB per 25 grams of A. Or I could do conversion factors between B and the compound. So 75 grams of B is 100 grams of the compound, or 100 grams of the compound per 75 grams of B. So those ratios or conversion factors I can utilize to jump between amounts of the substance and amounts of the individual elements, okay? So all you need is that percentage, and you can jump from grams of one thing to grams of another. So you can either calculate a percent composition of a compound on your own and then utilize it, or if that information is already given to you, you can utilize it that way. So let's look at a couple of examples of how this can be used, okay? So using a mass percent or a percent composition of a compound as a conversion. So first I give you the percent composition of, which I should have listed here. I guess I left that off. This is the percent composition of SCl2. Okay, and so I even show you how it's calculated. But I'm telling you that it's 31.14% sulfur and it's 68.86% chlorine. Okay, so that means any sample of sulfur dichloride contains that ratio, those proportions of sulfur and chlorine by mass. Okay, and I want to know what's the mass of chlorine in a 17.5 gram sample of sulfur dichloride. So what I'm going to do is I'm going to set this up as dimensional analysis. And I'm going to take 17.5 grams of SCl2, and I'm just going to focus on the units. I want to get rid of that grams of SCl2. That's not the information I want. I want mass of chlorine, so I want grams of chlorine, okay? And so the numbers that go in that ratio, I'm going to get from a percentage, okay? And specifically, since I want to know about chlorine, I'm going to look at the percent of chlorine, and I'm going to convert that into a ratio, okay? So that number you can place over 100. So it'd be 68.86 grams of chlorine per 100 grams of SCl2. So I'm going to put that in here, 68.86 grams of chlorine per 100 grams of SCl2. So that comes directly from that percentage. Alternatively, if you really wanted to, you could say that it's 0.6886 grams per 1 gram of the compound. Okay, I think it's easier, just take that number and put it over 100. Okay. So then that's going to cancel my grams of SCl2 and give me grams of chlorine, which is what I'm looking for. So 17.5 times 68.86 divided by 100, and that gives me 12.1 grams of chlorine. Okay, so that means there's 12.1 grams of chlorine in a 17.5 gram sample of sulfur dichloride. Okay, and so you can quickly just pull apart that information about a compound into the individual elements if you know the percent composition of the compound. We could do the same thing, use the same process to calculate the mass of sulfur in that sample. Okay, but instead we would use the percent of sulfur. Okay, let's look at one more. Oops, clicked too far. There we go. So this one, I give you, and again, I forgot to label this. It's the percent composition of lithium phosphate. Okay, so I give you the percent composition. I even show you the breakdown of where it came from. Okay, I didn't really need to show you where it came from, but just so you have that, so you have more kind of examples of calculating percent composition. So if you had this percent composition that it's 17.98% lithium, 26.75% phosphorus, and 55.27% oxygen, and you could utilize that information to answer this question that I give you. What is the mass of a sample of lithium phosphate that contains 1.85 grams of lithium? Okay, so I'm going to start with the 1.85 grams of lithium, and then I'm just going to look at it as unit analysis, do it as a dimensional analysis problem. So focusing on units. So I have grams of lithium. I want to get rid of grams of lithium. So I'm going to put it opposite. And then I want to know the grams of lithium phosphate. So I put that in my open slot. So now I'm relating lithium to lithium phosphate. So I'm going to go to my percentages and pull the lithium percentage because that's going to relate lithium to the total. And that 17.98 is the number of grams of lithium. So 17.98 grams of lithium in a 100-gram sample of the compound. So my grams of lithium will cancel, and that will give me the lithium phosphate. So I'm going to take 1.85, I'm going to multiply that by 100, and I'm going to divide that by 17.98. And that gives me an answer of 10.3 grams of lithium phosphate. Okay. And so that tells me that a 10.3 gram sample of lithium phosphate is going to contain 1.85 grams of lithium. Now, I guess in the end, you can go through and make sure that you did this right. You can check, and your percentage, you should be able to recalculate your percentage from that. So you could take 1.85 grams and divide by 10.3 grams. So the individual element divide by the total and then multiply by 100, and you should get the percentage back. That should come up with 17.98. So let's try that. 1.85 divided by 10.3 and then multiply by 100, and I get 17.96. Well, I rounded to 3 sig figs because my starting value was 3 sig figs. And my percentage, that means I integrated a little extra error in it, but it comes out pretty much the correct percentage, so we're okay. You can sometimes catch yourself if you made an error doing that, because if you made an error, it's going to be way off from the real percentage. Okay, so that's how you would calculate percent composition and how you would utilize percent compositions to then do conversions.